This is an example on calculating the electric potential and the electric potential energy of system of particles. We have several, more than 2 particles, and would like to find what is electric potential and what is the change in electric potential energy. So this is a question. The following figure shows 2 charges. Q1 is positive plus 5 multiplied by the charge of the electron, and the second charge, which is Q2, is minus 2 or minus double the charge of the electron. Okay, here it gives the charge of the electron as 1.6 10 to the minus 19. So this is a positive charge, 5 times this quantity, and this is twice this quantity. And it tells us that the distance d, this is 2d, where d is 2 centimeters, so this is 4 centimeters, my son. And this is d, which is only 2 centimeters. Theta 1 is 30 degrees, theta 2 is 60 degrees. Would like to find what is the electric potential at point A due to these 2 charged particles, Q1 and Q2. Okay, I want to ask you a question now. Is the potential, the electric potential, a scalar quantity or vector quantity? Your answer. What is your answer, my son? Is it vector or scalar? Yes, it is a scalar quantity. Does it matter where we place these particles in order to find the electric potential at A? Your answer is correct. It doesn't matter, okay, because the electric potential due to a charged particle is a scalar quantity. So there is no use of these angles, theta 1 and theta 2. It will be useful if he asks to find the electric field at point A due to these 2 charged particles. In that case, you need to know theta 1 and theta 2 because the electric field is a vector quantity. But right now, it is a scalar quantity. This is not necessary for us. We'll not use it in our calculation. We'll not consider it. What is the electric potential at point A? So we know that electric potential V is the summation of K Qi over Ri. Okay, so we are at this point. We want to know how much is this summation, K Q1 over R1 plus K Q2 over R2. Okay, so this will be K multiplied by Q1 divided by R1, which is 2D. Okay, we can take K as a common factor plus Q2, and here we put positive as positive charge. We plug its value as positive, and the negative charge we should plug it as negative as well. Okay, because it is a scalar quantity. Electric potential is a scalar. Whatever positive, you put it as positive. Whatever negative, you plug it as negative. And the separation between this particle, Q2, and point A is just D. So this will be Q2 over D. And plugging in the numbers, this will be 9 times 10 to the power 9, approximately. Sometimes we plug this as 8.9. But anyways, this is the way of calculating it. So Q1 is 5 times 1.6 10 to the minus 19 coulomb divided by 2 multiplied by 2 centimeters, because 2d centimeters, and this should be in units of meters. So this is 10 to the minus 2 plus, but this is negative, so this will be minus. Okay, twice the charge of the electron, so this is 1.6 10 to the minus 19 divided by d, and d is just 2 centimeters. You have to convert it to meters, and we'll end up with positive electric potential at point A. This is 3.6 times 10 to the minus 8, 10 to the minus 8 volts. What is this? This is the potential at point A. Nice. Part B. Calculate the work we must do in order to bring a positive charge 10 times the charge of the electron initially at rest from infinity to point A along the dashed line. So we'll bring it from infinity while it is at rest, and we place it at this point A, and its final speed will be 0 again. So initially its speed at infinity was 0, and finally its speed at A will be 0, and we bring that charge Q3, we place it here. So delta K is equal to 0. So this was our answer to part A. Part B, we know that delta K is equal to 0 because K initial is 0, K final is 0. Okay? So knowing that, he's asked about the work. How much the work done by whom? Work we must do. So this is the work done by external agent. You have to read the question carefully, my son. He might ask you, calculate the work done by the electric field. In that case, that will be the work done by conservative force. But now it is the work applied or work done by external agent. And we know that this is equal to minus the work done by conservative force, and this will be delta U. Okay, so the work applied is delta U. Now I'll answer this question in two different ways. Okay, so delta U can be written as Q3, which is the new charge will be moving, multiplied by the change in potential it will experience. Okay, so this will be Q3. Okay, where Q3 is this 10 electron charged particle, multiplied by V final. V final, what is V final? It will come to point A, which is VA, the potential at point A, minus the initial potential of this charge number 3. Initially it was at infinity, so minus V infinity. But how much is V infinity, my son? V infinity, we know by choice, by definition, it is equal to 0. So I am left with this. Just multiply Q3 with VA. This will give you the work done by external agent to bring Q3 from infinity to point A. Okay, so this will be 10 multiplied by, it is 10 E, so this is 10, 1.6, 10 to the minus 19, multiplied by VA, and VA we have found in the previous part 3.6, 10 to the minus 8, and you will end up with a result 5.76, 10 to the minus 26 joules. Okay, this is the work done by external agent. Okay, طيب, what will happen if he asks us find the work done by the electric field? What will be our answer? Find the work. I am done. I have answered part B, but let us ask it in a different way. Find the work done by the electric field to bring Q3, which is plus 10 electron, from infinity to point A. It is the same question, but not the work we must do, the work done by the electric field. What will be the answer? We know that the work done by electric field is the work conservative. The work conservative is equal to minus delta U, which is minus the work done by the applied force, and this is true because delta K is equal to 0. So our answer here will be shortly minus 5.76 10 to the minus 26 joules. Okay, this is the answer for this extra part. I promised you to solve it in a different way. Can we answer this part B in a different way? Yes. Let us see how to do it. I'll go another method to answer part B. Here I said work applied equals delta U, and delta U is Q3, which we have moved, multiplied by the change in its electric potential. Okay? Now I'll do it in a different way. Work applied equals delta U. And delta U is nothing but U final minus U initial. What is the potential energy of our system finally when we brought particle 3 and placed it here? This is the final situation. Minus the electric potential energy of the system when the charge number 3 was at infinity. Okay? So this will be the following. Equals U final of the 3 particles in this figure. Let me draw it here for you. So U final represents, I hope it is clear in the camera, represents this situation. This is plus, this is Q1, and here we have point A, and here we will have our charge, which is Q3, and there is our negative charge, which is Q2. Here we have distance D, and there we have distance which is 2D. Okay? Then finally, this is the final situation. What is the initial situation? So U initial represents what? Represents the following situation. I had only Q1 here, and this place was vacant, okay? And here we have Q2, which is negative. Q3 is very, very far away. It is at infinity. Q3 is there very far away at infinity. Okay? If we find U final of this configuration, U initial of this configuration, the difference between them should give us the same difference, which is equal to the work done by external agent. Okay? So how much is the electric potential energy of this system finally? Okay? So the potential energy will be K Q1 Q2 divided by the distance between 1 and 2, okay, plus Q1 Q3 divided by the distance between 1 and 3, okay. Distance between 1 and 3 is just 2D, okay, plus Q2 Q3 between this divided by the separation between them, which is D. This is the distance which is R1. This is the distance R12, which we don't know. Okay? So this is U final. What is U initial? If we find U initial of this situation, it will be only 2 particles. The third is at infinity, so it doesn't contribute to the electric potential energy of this system because it's very far away and it doesn't affect our system. So this will be K Q1 Q2 divided by R12. Okay? What will be the difference between them? So the work applied will be U final minus U initial. If you look here, what will be the difference? This term is the same as this term. So this term will cancel with this term. And we are left with the following. We are left with K Q1 Q3 divided by 2D plus Q2, okay, Q2 Q3 divided by D. I can take Q as a common factor outside, so this will be Q3 multiplied by K Q1 over 2D plus Q2 over D. But look, what is this? K Q1 over 2D, K Q1 over 2D plus Q2 over D. This is nothing but VA. So I'll end up with Q3 multiplied by VA. Okay, so this is Q3 multiplied by VA, and you will end up with the same result, which is 5.76 10 to the minus 26 joules. So my son, you can choose whatever method you would like, whether the work applied is Q delta V or the work applied is the change in the potential energy. Any method will lead you to the same answer. Thank you. This is another application for finding the electric potential of a system of charged particles. Here we have a rectangle shown. The sides have length of 5 centimeters and 15 centimeters. So this is 15, that is 5. Q1 is placed here at this corner and it is negative minus 5 microcoulomb. Q2 is positive and it has magnitude 2 microcoulomb. With V equal 0 at infinity, this is by definition, and this is our choice for this course. What is the electric potential at corner A? Here, we want to know how much is the electric potential at corner A. Okay, then what is the electric potential at corner B? Okay, then we want to find how much is the work we must do in order to move a charge Q3 from corner B to corner A, okay, along the diagonal of the rectangle. So we'll move it starting from rest. It was, we'll start by Q3 having 0 speed here. We move it and bring it there and keep its speed to be 0. Okay? Let us start with part A. Part A, what is the electric potential here at this corner? So at this point, we have contribution coming from the negative charge, okay, and another contribution from the positive charge. And the electric potential is a scalar quantity. So V at corner A equals K, okay, Q1 divided by this distance, which is 0.15 plus Q2, and we have to plug Q1 and Q2. Whatever positive, we plug it positive. Whatever negative charge, we plug its value as negative. Divided by 5 centimeters, which is 0.005. Okay? Plug in the values. This will be 9 times 10 to the power 9. Q1, which is minus 5 micro, 10 to the minus 6, divided by 0.15, plus Q2, which is 2, 10 to the minus 6, divided by 0.05, and we'll end up with VA, which is positive in this case, 6 times 10 to the minus 10 to the power 4 volts. Okay, this is V at point A. Let us do the same for corner B. What is the electric potential at this point here? There is a contribution from Q1, contribution from Q2. Will we have the same electric potential as that at point A? Not necessarily, because now Q1 is closer to this point, while Q2 is far from this point. Here, the opposite. Q2 was close to A, while Q1 was far. So we don't expect to have the same electric potential at point B. So VB will be K. Now Q1 is divided by 0.05 because Q1 is only 5 centimeters away from corner B, plus Q2 divided by 0.15. Okay, plugging in the values, here we will get VB to be negative because we are closer to Q1, which is negative. So we'll have more negative contribution than the positive contribution of Q2, and we'll end up with minus 7.8 times 10 to the power 5 volts. Okay, this is V, this is VB. Now we are ready to answer question number C. What is the work applied in order to move particle Q3 from point B to point A? And I think now you can easily notice that we can answer this question in two ways. The first way, that the work applied is equal to minus the work done by the electric field, work conservative, and this is equal to delta U, because we can tell this because delta K is equal to 0. So initially Q3 was sitting here at point B. Finally, it will be sitting at rest at point A. So delta K is equal to 0, and the work applied will be equal to minus the work conservative, and this is equal to delta U. So the work applied will be equal delta U, but delta U is nothing but Q3, which will be moving, multiplied by the change of its electric potential. Okay, so this can be achieved by multiplying the magnitude of Q3. Q3 is positive. Yes, it is positive. Multiplied by the change in its potential. So initially it was at point B. Finally it is at point A. It moves from point B to point A. So finally it is at A. Initially it is at B. Be careful. You have to read the question carefully. If he asks you to move it from A to B, so you have to reverse. It will be VB minus VA. But now he is asking to move it from corner B to corner A. Okay, plugging in the values, we'll get the following. This is 3 times 10 to the minus 6, Q3. VA, which we found to be 6 times 10 to the power 4, minus VB, which is minus 7.8, 10 to the power 5. Okay, so minus, this will give us plus, and we'll end up with a positive work equal to 2.5 joules. Okay, so this is the work applied. What is the other method, my son? Another method to answer this question is that the work applied equals delta U, which is U final minus U initial. Let me draw here for you, as we have done before, what was U initial and what was U final. U final is like this. We have Q1 at this position, okay, and we have Q3 sitting at A, okay, and we have Q2 sitting here. This is the final situation, okay? So this distance is 15 centimeter. This distance is 5 centimeters, and we can find this distance using Pythagoras, and I call it R12, okay? So this is the final situation. The initial situation, U initial, can be represented by the following. Same thing, we have Q1 sitting here. Here, this side was vacant. We have Q2 sitting here, and Q3 was at this point B. Okay, so this is the initial situation. Okay, so this is same R12, and this distance is 5 centimeters, and this is 15 centimeters. Okay, this is the final situation. This is the initial situation. How much is U final? U final will be K as a common factor, and we have Q1, Q2 divided by R12 plus Q1, Q3 divided by 0.15. Okay, plus Q2, Q3 divided by 0.05. This is U final for this situation. For U initial, we can tell that it will be K Q1, Q2 divided by R12. It is the same as the final situation, plus Q1, Q3, and now the distance is just 0.05 plus Q2, Q3 divided by 0.15. If you find U final minus U initial, what will cancel? This term will cancel. Okay, and we are left with the following: delta U, which is the work applied, equals delta U, which is U final minus U initial, and we are left with the following. K will be a common factor, and we have a Q1, Q3 divided by 0.15 plus Q2, Q3 divided by 0.05 minus Q1, Q3 divided by 0.05 minus Q2, Q3 divided by 0.15. If we take Q3 as a common factor, okay, so Q3, I'll take it out. Are you following? Q3, I'll take it out here as a common factor. And you can tell easily that Q1 over 0.15 plus Q2 over 0.05, what is this? This is the VA, okay, minus Q1 divided by 0.05 plus Q2 divided by 0.15. So this can be written as Q3 multiplied by V at point A minus V at point B. And we'll end up with the same result, which is 2.5 joules. I think, my son, now you understand how to find the change in the potential energy. Whether you find the total potential energy finally of your system and the total potential energy initially of your system, find the difference between them, or alternative way, find Q, which will be moving, multiplied by the change in its electric potential. So these are the two alternatives. Whatever you find convenient for you, you can use for solving your problem. Thank you.